It was Friday night. I was trying to finish one of my first tasks. I logged into the controller and it basically took down the whole cluster. Everything was failing, red alert all over the place. I was like the new guy. I remember thinking that's it, I'm done. My friend and I, Leandro, we wrote maybe a draft of a blog or two. And then I got ambitious and said, well, why don't we just write a book? Leandro was like, yeah, why not? Let's do it. I cold emailed Tom Wolfe saying, hey, we're writing a book. We're big fans of Hugging Face, blah, blah. And so we actually started our first contact with Hugging Face through this book project. One of the things I sort of learned that part of being a very effective data scientist is actually not about training the best model, but finding the simplest solution to the actual business problem.
When I started my first job, I asked exactly the same question to my manager. Why don't we use deep learning? And then you realize that deep learning is not the answer to all the questions. Very often simple algorithms work and Excel can also work.
The way you can actually build such representations is using a different objective, which is called masked language modeling. So if you have a sentence like, my name is Lewis, you might mask out the word name, and now you get the model to now predict what would be the missing token in that sequence. It's fair to say that without ChatGPT, the LLMs of the world would not probably even look like anything like they do today.
This episode is brought to you by Training Data. If you're new in data science and want to get into the field, or if you're already in the field but want to progress, well, Training Data is the platform for you. They offer courses on feature engineering and selection, model tuning, interpretability, and much more. You will get both the math and the intuition behind each method, but also Python code ready to power your own projects. So if you're interested, visit the link in the description and don't forget to use the code AI Stories to get a 10% discount. All right, so hello everyone and welcome to the AI Stories podcast. I'm Leiser, I'm a senior data scientist and I will be your host. So today our guest is Lewis Tunstall. Lewis is a machine learning engineer at Hugging Face working on LLMs, and prior to that he had a lot of experiences. He got a bachelor and a PhD in theoretical and mathematical physics from the University of Adelaide. He worked as an ML engineer, as a lead data scientist. He contributed to open source. He wrote a book, Natural Language Processing with Transformers. And we're going to talk about all of this in this episode. So we'll talk about working on open source libraries, about LLMs alignment, deploying LLMs. If you enjoyed the episode, please subscribe to the AI Stories YouTube channel, comment, share, and leave a 5-star review. All right, so let's start now. Hi, Lewis. Hope everything is going well for you. First thing I wanted to ask is, how did you get into this world of AI and machine learning? How did you get into the field?
Hey, Neil. Thanks for having me. I would say the journey was completely unplanned and somewhat random. So when I was younger, I was very much into physics and especially into theoretical physics. And I always thought my kind of journey would be the academic path of doing a PhD, then a postdoc, and then a professor. And when I came to Switzerland to do my postdoc, I had a couple of friends who were working at the Large Hadron Collider in CERN, and they were analyzing different algorithms for essentially how do you classify the signal from the background when you're looking for these new subatomic particles. And they were sort of very excited about the role that this new technique called deep learning was having. And this was around 2013, 2014. So deep learning was kind of going mainstream, but it wasn't yet like what it is today. And they were like, hey, check out this this thing we've done. It's a few hundred lines of Python, and we can kind of outperform all the handcrafted features that physicists had developed for the past 3 decades. And I was very much like a theoretical physicist, so I didn't even know how to program very much. And I remember being quite surprised that this sort of 100 lines of code could do so well. And so I thought, well, maybe it's good to have a look at this just for fun. It's quite intellectually interesting. And it coincided with one of my friends saying he would like to tackle a Kaggle competition as a way of, honing his skills. And so this was my very first taste of machine learning, where we competed in a Kaggle competition to basically predict the housing prices in Moscow. And again, this is funny because like in 2014, I think, or 2015, almost all Kaggle competitions were tabular. And so basically everything was like XGBoost and, these kind of tree-based methods. And as someone who was coming kind of fresh into this, it was actually a pretty nice onboarding because you could run everything on your laptop. You only had to work with tables. It was kind of easy. And then after doing that competition, I just found myself getting more and more kind of excited and interested in the field.
Actually, on that competition, I've got a few questions already. First one is, how did you know which algorithms to use? I mean, you're new to machine learning. You don't really know about the field. How did you know which algorithms to use, and how did you learn about those?
Oh, yeah, that's a great question. So I think I did what most people do, which is like you start with the Titanic data set. And on Kaggle, they actually have a lot of notebooks like from the community where people show different applications of different algorithms for these methods. And I remember in one of the Kaggle notebooks, they were showing like how to use XGBoost. And at the time, I had no idea what XGBoost was. So I was kind of doing, I think what maybe most people do, which is like, you know how to make it work, but you don't know how it works. And then the other thing was that in the competition itself, many people were sharing their like kind of preliminary solutions, which I think is something quite special about Kaggle, where people are quite open, even though it's a competitive environment. And this was where like I started learning about ensembling and all these like kind of, methods, again, not fully understanding how they work. But it was the start of, like trying to sort of understand, maybe this is a field where I could, do something interesting. And after that competition, I started trying to learn more, and in particular, this was in the old days where there was only TensorFlow 1 for deep learning, and so I remember I started just doing. I think there's a kind of famous book called Hands-on Machine Learning with Scikit-learn and TensorFlow from Aurelia and Jaron, and this book was sort of then my entry point into sort of deep learning. And it came around the point where my postdoc was finishing. And in academia, you usually have this kind of journey where you do multiple postdocs, hoping eventually to find a kind of permanent position. And it just so happened there was a startup opening up right next to my house. And I thought, well, this is an interesting field. They're looking for a kind of data scientist. Maybe this is a chance to do something very different. And so I switched basically from academia, kind of like a very hard pivot into industry. And the startup actually was I think, the situation that many people experience when they do their first data science job, where you think, oh, it's going to be like Kaggle, but using like real data, and I'm going to train like 100 models and stuff. And then I remember when I started at the startup, because they were a startup, they're like, well, we don't actually have any data yet. We're building out both, the sort of infrastructure layer, but also the connections with customers to do this. And so my actual, I would say, first maybe year or year and a half of being a data scientist was actually not doing data science so much. It was really more data engineering. And personally, like, in hindsight, it was like a really good thing because I learned a lot of like good software engineering skills. But I do remember at the time thinking, oh man, like, is this what data science is? Like, this is not what I expected. And so this was sort of, like I would say my entry point. And then after that, I remember a friend of mine.
Sorry, on this side, on data engineering, can you give examples of things you worked on? Like, what do you call data engineering?
Yeah. So this startup in particular, they're called Spout. They're still around in Switzerland. And what they focus on was what was called stream processing. So basically around 2015 or so, there was a very big like kind of move in industry going from big data, which had previously been built on like a stack using Hadoop and other things like this and Spark, to how do you deal with data that is essentially real time. So for example, this might be data coming from like, sensors. It might be data that's coming from, let's say, people placing bets on games. And the startup was focused on how do you basically essentially build a platform for this like new streaming data. And so specifically the kind of things I did were using a stack called Kafka. It's a framework that is quite common nowadays for dealing with streams. And then using these like kind of Kafka streams of data to do some business logic. So this would be things like aggregating multiple streams together to compute various metrics. And in particular, we were often working with essentially logs from like applications. So you have companies which have, thousands of applications. They all emit logs. They're all kind of connected in some complicated way. And then kind of building out like the topology of that network so that then the DevOps engineers could kind of very quickly visualize, okay, we have a failure in this part of the network. We need to drill down into that and understand what's going on. And this is very different to like conventional, let's say, static data engineering, because once you have time in the problem, a lot of your thinking about like how you do aggregation has to change because you now have to worry about drifting in time. So this was like a pretty hard, I would say, entry point. But I was very lucky that the team, was very interested in like training new people like myself, and so this was kind of where I got my first, let's say, hard experience in the land of data science.
And you mentioned that you hoped it would be like Kaggle, you hoped you would train model, and you didn't. I feel like there are a lot of companies nowadays that say they need to hire a data scientist and then they don't have the data, or data scientist is just playing with Excel. So what are the things you can do? What are the things you did in the future to make sure that your next job you would do actual data science?
Yeah, that's a really good question. So what I was always trying to do was sneak in some sort of like analytics into the problem. So usually the way this worked well was if you have a customer who you can build some degree of trust, which typically involves first solving the problem that they want. This often gives you the sort of entry path to then saying, well, I know there are these other issues that your team is facing. Let's build something together. And one thing that we did, which was quite cool with one of our customers, was they had this very, very large application network. And we had built this kind of topology where you could very easily see, which parts of the network were failing. But the DevOps engineers said, it's really annoying because we basically get like phone calls, like, we sort of don't detect it in advance. We sort of only see it happening after we're told, and then we use that to find the issue. And they said it would be really nice if there was a way to sort of either predict or at least, detect as early as possible something is going wrong. And so this was a sort of one of the first actual data science projects we did, where we built essentially an anomaly detection system for them. And it was a really kind of cool real world project because the latency constraints were so extreme. Basically, you've got all these coupled applications talking to each other on the millisecond timescale that all the deep learning stuff was off the table. And in the end, we built a very simple kind of statistical system to kind of sort of forecast if there were going to be deviations in various metrics. But this worked quite well, and this was like my sort of entry point into doing actual ML, which then later on when I did other jobs was a nice sort of discussion point.
Okay, but what I meant was more like, how do you make sure that when you start a job, you're actually going to do data science, or you're not going to end up in a company that does only data engineering?
Yeah. Gotcha. Yeah, I think that's a bit harder. Maybe like the thing that later when I was applying for other jobs that was often a better signal was to actually talk to the data scientists in the if not in the team, but at least in the company. And they would often give you, I think, a more accurate representation of what is actually done. I think often at the sort of management level, there's not maybe a deep understanding of like all these sort of technical issues and what is actually data science. It's kind of not a super well-defined term. But yeah, trying to talk, I think, to people who are like actually doing the work. And the other thing that I often found was a good signal is if these companies would publish some kind of, let's say, technical reports, or if they published, for example, in Switzerland, we have a yearly conference with all the industry doing different applications of ML. And it's this is where you can actually see which companies in Switzerland are actually using machine learning in the real world. And that's a good signal.
Yeah, no, that's a good point. I also, during interviews, I always try to ask what are the projects that the team are working on, because by understanding the projects that they're currently or that they've worked on in the past few months, you directly know whether, if they say, oh, you need to do an analysis in Excel or something like that, you're not going to be a real data scientist. And maybe Excel is what you want, and then you found the right place. But by understanding the kind of projects that the team or the company has worked on in the past, you would know more or less what you're going to work on in the future. So I think it's really important to ask those questions in interviews.
Yeah, absolutely. And I think one thing, at least for me personally, so I was a data scientist for maybe 4 or 5 years before I eventually joined Hugging Face. And I think one thing I learned is that with experience, often the simplest solution is actually the best one. Mm-hmm. And the simplest solution may be actually Excel, or it may even be SQL or something like this. And when you're young, you want to do all the cutting edge stuff. You want to let's get some massive neural network to solve this problem. And that's partly because that's the most intellectually kind of, let's say, attractive thing. But then when you have to deploy this stuff into production, then you face a whole range of new constraints that don't exist, offline. And then you start really, if you're the one who has to maintain the deployment, then you also want to make sure that it's simple to debug. And I think that's one of the things I sort of learned, that part of being a very effective data scientist is actually not about training the best model, but finding the simplest solution to the actual business problem. And that requires, a slightly different maybe skill set than, your conventional, model trainer.
Yeah, no, I 100% agree. And it's funny because this week actually, so I work at Artifact and I've got a few clients, and they hired a new intern. And the first thing this intern asked me, because she just joined this week, is I built some models and I have very little data points, less than 100. And she asked me, why don't you use deep learning? And she reminded me of me when I started my first job. I asked exactly the same question to my manager: why don't we use deep learning? And then you realize that deep learning is not the answer to all the questions, and very often simple algorithms work, and very often Excel can also work if you've got non-technical stakeholders and you need to communicate your results in an easy way. Giving them an Excel file can be a great way for them to understand what you've done. So I definitely agree with you that deep learning is not the answer, and sometimes Excel can do the job quite well.
Absolutely.
And so, okay, I went a bit on a tangent here, but so you worked as a data engineer for a couple of years, and then you moved to more traditional data science. So can you talk a bit about your experience working in data science?
Yeah, sure. So after I had done this for a couple of years, I felt that I had kind of mastered relatively well all this streaming systems, and in particular how to do distributed data processing at scale. This was quite interesting. But I always felt I wanted to do more of that sort of classic ML type stuff. And as a coincidence, one of the guys I shared an office with when I was a physicist in Bern, he was basically starting a new company with a bunch of mathematicians who wanted to essentially apply various algorithms they had developed for clustering, or essentially for doing sort of unsupervised learning, to kind of real world problems. And so they said, maybe you can bring your software engineering skills into this kind of very math heavy stuff, and maybe we build something interesting. And so this was a startup called Learn to Forecast. And we built one of the sort of first, let's say, open source libraries for a branch of machine learning called Topological machine learning. And we can talk about, what that is and why it's interesting. But this was essentially, my first kind of experience, both doing implementing algorithms from scratch, but also trying to build a community, and also trying to build open source software that is robust and well tested. But yeah, happy to go in any one of those angles, whichever one you think is interesting.
Yeah, keen to dig further into, those two angles. Actually, let's start with the first one. What's topological machine learning, and can you go into the details of what you've built exactly? Why is it useful?
Yeah, sure. So I would say topological machine learning can roughly be thought of as a type of unsupervised learning. And in particular, it's a kind of niche subset of academic research. But what it's concerned with is, how do you have a principled way of understanding the structure in essentially point cloud data? So a large amount of data in the world is represented as point clouds. So, for example, anything from like embeddings to tabular data to data that's on a map, anything like this has some sort of point cloud structure, or self-driving cars even, if they're doing LiDAR, they have a lot of point clouds. And the question that topological machine learning tries to ask is like, okay, if I want to understand if there's some structure in this data, what can I do, and how can I do it in a sort of rigorous fashion? And so the sort of simple thing you do is clustering, right? Like that's what we all use. We have various clustering algorithms. And these clustering algorithms, they often have some parameters, like these like hyperparameters that you often have to tune. And actually identifying what clusters have meaning is a little bit of like, let's say, a human skill, right? So you have to tune, for example, if you're doing like k-means clustering, you have to tune the k and stuff like that. And so what topological machine learning tries to do is it tries to essentially remove this like dependence on hyperparameters by studying the topological structure of these point clouds. And this lets you identify robustly if there are, for example, holes or voids or things like this. And to give you an example of something like what this might mean is you might have, for example, a time series which has some kind of periodicity in the signal. And what you can do is you can embed that time series into a high dimensional space, and then you can check whether this high dimensional space has the structure of a ring. And that structure will then tell you that there's a certain periodicity in that time series, and you can actually calculate properties of that kind of topological space, which tell you, elements that then, what type of period it has, is it aperiodic, stuff like that. And so it's essentially, you can think of it as a collection of algorithms that let you take this kind of point cloud data and generate these topological structures. And, we can go really deep into how it works, but roughly speaking, it's an alternative to clustering. And it found a lot of success, I would say, in like the early 2000s. A bunch of US companies had used it to detect quite novel things in the structure of like US elections and so on. And what we wanted to do was essentially bring a lot of that kind of custom knowledge into the world of open source. And so we built a library called giotto-tda for topological data analysis. And it's kind of like a scikit-learn like library, but it really implements the kind of largest collection of such algorithms.
Can you go deeper into the inputs and outputs of, let's say, the library or the topological algorithm? Like, is the input a time series, for example? Or do you need first to embed it with another library and then pass this input, this embedding to the topological algorithm or to your library? And also, what are the output? Is it a graph, like a ring, as you mentioned, or is it, I don't know, also some numbers that would say, hey, the periodicity is A or something like that? So yeah, can you give more details about the inputs and outputs that need to go?
Great question. Yeah, so basically speaking, you can think of it as like a feature extraction pipeline. So the goal is that given some inputs, you want to produce features which you could potentially combine with other features and then train a classifier or some regressor on top of that, as you would in normal, like kind of supervised machine learning. The inputs can be quite varied, so they can range from like a sort of, let's say, a raw time series to images, to graphs, to point clouds. It's fairly agnostic, but basically what you have to do is you typically have to do some form of pre-processing, and that is a little bit dependent on the algorithm that you're studying. And so the library effectively abstracts that pre-processing step, so that essentially if you want to apply a certain type of algorithm, you just have to provide the raw input, and then you get these features. And these features are what are called topological features. So if you imagine that I have, let's say, a point cloud, and imagine in that point cloud, there's a structure that's like a donut, something like this. You can actually encode that structure mathematically using a sort of part of mathematics called homology. But in a nutshell, what you're basically measuring is like, is there a hole in this data? Or is it a sphere which has no holes, or is it, there are even high dimensional analogs. So there are different ways of these so-called topological or homological invariants. And what this pipeline does is it allows you to take your input and then compute these topological invariants And then those invariants can be used to then train, say, a classifier. So you could imagine I might have, say, two different point clouds, and I want to be able to classify if they're different.
Okay.
And these topological features, they give you a very strong signal on whether or not they truly are different. And one project I worked on was to actually use this to distinguish like gravitational wave signals from background, where basically, every day there's like gravitational waves passing through the Earth. And this experiment in the US has collected a lot of this data, and it's a really noisy time series. Like if you look at a time series that looks like a gravitational wave and you look at a signal, which is the background, it's just super, super noisy. But within these gravitational wave signals are some of these topological structures, and then you can extract them using this like feature extractor and then train a pretty robust classifier.
Okay, very cool. And you mentioned it could also be applied to US election. How does that work then?
Yeah, so this one's a slightly tricky one. Basically, there's a particular type of algorithm called mapper, which is one of these kind of like clustering algorithms. And basically what you can do is you can look at like the voting districts. So you look at the map of the US and you've got like certain features associated with like the way people vote in each of those districts. And so these features, like they can be things, for example, like, the demographic information. They can be things about, let's say, how they voted in the past few years, stuff like that. And so this effectively gives you like a tabular data set with all of these things. And you have a categorical variable which encodes, which state you're looking at or which district. And then if you apply this mapper algorithm to this tabular data, the result is a very kind of beautiful looking graph, basically, which tells you, roughly what kind of influences or which features will potentially influence the voting decisions. Because essentially you can look at these clusters and you can say, okay, these clusters are dominated, or this cluster, for example, was, let's say, voted Democrat, and the features which most influenced that were coming from these, say, demographic components. So essentially it's a way of having a notion of clustering plus interpretability, which lets you, make some decisions about, if you're a party, you might want to use that to, figure out which voters to target and so on.
Okay, very cool. Very interesting topic. I didn't know about topological ML. So that's, quite interesting. Is it still very popular nowadays? Do you know?
It's quite popular in France, actually.
Okay.
Almost all the pioneers are from French universities and from INRIA. But I would say it kind of came at a time when Transformers landed. And I think it's just very hard to, get any kind of traction or, let's say, consciousness around, new methods outside of deep learning and Transformers. And I know that lately, some researchers, they extended this idea of, like a kind of feature extraction pipeline to having differentiable layers. And they had some cool results where, for example, if you're training like a UNet to do, say, image segmentation, when you have these images, like in medical domains, you may often have topological structures. Like you imagine you're trying to segment like the aorta valve or something in a CT scan or something. Then, you can encode, you can have a layer in your neural network, which will then kind of essentially pick up these topological structures and then, make the sort of sample efficiency of the training much better, which in medicine is useful because you typically don't have a lot of labeled images. So I think there's like some applications in that case, but I would say that, Transformers kind of took over.
So before we talk about Transformers, we're going to talk about it quite a lot. The second, let's say, point in this topic is open source. You started contributing to open source. You're now at Hugging Face, so you're working on open source as well. So can you give me your view on open source? What is it like to build a community, to build something open source? Why do you like it so much? Why do you think it's important for the ML community? Keen to get your view on that.
Yeah, sure. So for me, it was funny when I worked on this giotto-tda library, because I had, I think, never up until that moment contributed to anything to open source. I was very much like a user in the sense that like I had like pip installed, XGBoost and stuff, but I had never done that extra step of thinking, you could actually contribute back to the software. And when I was building this library with my colleagues, what I really liked was this notion of interacting directly with people, very random people on the internet, basically. But you have this feeling that you're helping, make the world a better place in a small way, because these things are not groundbreaking per se, but you have this sense of doing something that is genuinely helpful, and it's like it personally makes me feel good. And the other thing is there's an element of, let's say, education, usually associated around open source. So like you have to kind of figure out how do you teach people how to use these tools. And, all throughout, even when I was a physicist, one thing that I was very passionate about was teaching people and, helping them understand complicated things as simple as possible. And so open source kind of blends a bit of that kind of educational component with the sort of building tools to help people component. And it feels like, a kind of very pure type of thing to do. Of course, there's many, open challenges, how do you sustain this long term and so on. But nevertheless, I think that's like a useful part. And in the context of machine learning, I think it's fair to say that without open source software and now, open weight models, open data sets and so on, the field would look completely different. So like maybe as a kind of analogy, like in when I was a physicist, there was like a lot of software that was written, which was kind of open source, but it was often like, you had to email the guy to get some code, and it was like Fortran, and it's like, oh my God, how do I even use this? And in like a very like, publicly visible open source community, you really see the rapid rate of like self-improvement and progress that is made towards, training better models, building better data sets, building better tools. And this is kind of like the collective consciousness of the world almost all together at once trying to do this. And so it feels to me that like, if we didn't have like a very vibrant community, we wouldn't have PyTorch, we wouldn't have maybe Transformers, we wouldn't have all these things. And so that would, have translated into a world where we wouldn't have Llama, we wouldn't have Mistral, we wouldn't have, very big data sets. So I think it's a very important component of the ML ecosystem. And it's one that Hugging Face tries to cultivate and protect a bit.
So let's make the parallel, the transition between open source and LLM by talking about open source LLMs. There are kind of two camps in the LLM world today. There are like OpenAI, Google, who have like closed source LLMs, and then Mistral, Meta, other companies who build open source LLMs. What's your take on this? Do you feel that we need both today? Do you think that in the future open source will be the way to go? Yeah, what do you think about open source versus closed source LLMs?
Yeah, it's a bit of a tricky question, but I would say so. First of all, people like to give a lot of, let's say, shade to OpenAI and Google, saying, oh, they don't open source things, especially OpenAI. But I think we have to remember that they open sourced GPT-2. They open sourced Whisper, which is like the best, speech transcription model in the world. So they're of course, quite selective about what they open source, but what they do open source often has a very large impact, and I think a positive impact. And Google, I think, lately has changed its perhaps strategy. So they seem to be really embracing a much more open source ethos. So there's like the Gemma models. They just recently released PalyGemma, so like a multimodal extension. And I think that's more like a response to Meta to sort of find a way where they can, show that they're still in the game of open source as well. But as to your broader question, I kind of feel that it's like the future looks like one where both it kind of coexist in a sort of, I would say, symbiotic relationship. So it's fair to say that without, say, ChatGPT, the LLMs of the world would not probably even look like anything like they do today. And all this like amazing innovation around how do you have large context? How do you run things in like low bit quantization on, gaming GPUs and like all this kind of stuff? It really comes from like OpenAI showing the world, hey, if you build this technology, it's pretty amazing, right? So I think we tend to, I think, still need like the sort of proprietary models to sort of show what's possible. If you have, very huge amounts of compute, very large amount of data. And then what the open source ecosystem typically does very effectively is they take that kind of proof of principle and then they really run with it and find ways to, say, reverse engineer it, or at least innovate so that it's like smaller models, or more efficient training techniques, which I think is beneficial overall. I would say the one thing I am not super a big fan of is that there is this like large discussion around like regulatory capture and like whether or not you should be allowed to train models larger than 10 to the 26 teraflops. And these things, they're a bit difficult for me to view without a cynical like perspective, because historically we've seen when large companies want to monopolize a market, they go straight for the government. And so my hope is that this ecosystem, or this symbiotic relationship, will evolve into something that's like much more like we've previously had with the internet and other technologies, where you still have regulations around like the applications of such technology, but the core technology is not itself regulated out of existence. But that's to be seen.
And maybe a naive questions for those not that familiar with the field, but like nowadays GPT-4o is probably one of the most performant algorithms. So why is open source useful, and why do we still need those open source models? Can you give your view on why those models are still quite important today?
Yeah, I think they're important for a couple of reasons. So the first one is that the open source models, so for the listeners who maybe are wondering what we're talking about, these are essentially like files that you can download on your laptop, or if it's too big, you download it on a bigger machine. But they're basically files that can essentially execute some sort of, say, text generator or computer vision system or something. And basically, once you have these files, you're the owner of them in some sense. Like you can keep them frozen, which means that your predictions will basically be relatively consistent over time. And that's something you can't control with, like, say, a dependence on an external provider, because OpenAI and other companies, they're updating their models and making them better. But then, if your whole product is built on top of these APIs, you can get a big distribution shift when they roll out a new checkpoint. So the open source models, they have that ability to kind of give you more reliability in that respect. The other side of it is that from a research perspective, all this innovation that we've had, as I mentioned, around shrinking models, making them train more efficiently stuff, that's only been possible because there have been good open source language models that you could then tinker with. And what that means is you actually have to have access to the weights of the model, so you can actually then tune it and so on. And I think, ironically, like a lot of the research that's gone into how do you make language models behave in a sort of more targeted way. So if you want your models to, for example, not emit toxic stuff and things like this, a lot of that research has actually, again, been pioneered through open models, because, again, you can take open models, you can figure out like, okay, how do I break them? So like Llama 2, for example, it has certain safety filters. You can figure out how to break them. And then you can figure out, okay, how do I make it now robust? And that stuff, that kind of research, I think, is extremely hard with just an API. And maybe the third element is this idea of like kind of democratizing access, or, democratizing is a bit of a loaded word, but like you could imagine this idea of like, how do you make technology as widely accessible to people all over the earth? And open source ML, in a sense, provides that, because, you can get these models, as I mentioned, you can download them from Hugging Face, you can run them on your laptop, and you can, in the not too distant future, I think, train them with like your laptop's kind of compute relatively fast. So I think this is like a trend where, almost anyone will be able to then have the ability to have their own kind of personalized AI systems. And that then minimizes your dependence on just a few providers, which, they have their own choices they make about the kind of personality and capability of their models. But this gives you much more kind of fine-grained control. And so I feel like those are roughly maybe the three big things of why it's important.
And is there also like a security thing, because it's your model, you control it more, and so it's safer? I mean, you can deploy it on-prems, for example, and you're sure that everything stays in your control. I know a few banks, they they like to deploy LLMs on-prems just to make sure their data is safe. So is security also a good point?
Yeah, I think so. I think it's a question of like whether you think your security team is better than OpenAI's.
Yeah.
Maybe that's like the thing. But I would say that in general that there is like a concern of like if you have very sensitive data, like in a bank or in an insurance company, then sending that data to an API entails certain risks, and those risks may be mitigated if you deploy on-prem. I suspect though that having seen what Azure and AWS are doing with Bedrock, basically these models like OpenAI's ChatGPT and also Anthropic's Claude models, they are progressively, I think, getting more integrated into the kind of cloud regions where your company may be running, and so part of that concern is mitigated. But another way of also looking at it, not just about security, is like if you're a company that is trying to like differentiate itself from other companies, then using APIs will give you maybe some of an advantage, a competitive advantage. But at least today, the ability to sort of train your own models is still like a relatively not so easy thing to do. And so that gives you a little bit of an edge today that you can, really tune models to be very performant on certain tasks, which you won't easily get from a general language model, even GPT-4, right? Like there are several examples where you can fine tune a code model, open source, that is better at converting, text to SQL, and, it's much cheaper, stuff like that. So.
Yeah, no, that's a good point. I agree. You can make open source model really good on very specific task, whereas like open source, closed source models are more like generalists. They can do a bit of everything, but if you go on a particular niche, then open source models might be better. So I want to talk about your work now at Hugging Face. And before we talk about this, can you just explain how you started joining Hugging Face? How and why did you join the company, and how did you start working on Transformers?
Yeah, maybe I'll start with how I started working on Transformers, which was again a somewhat unplanned thing. So I mentioned earlier that when I was working on this like topological machine learning, like Transformers kind of landed on the scene and made a splash. But because I wasn't working in NLP, it was like still outside my radar. And at this conference I mentioned, is this applied machine learning conference in Switzerland, there was Jacob Uzkoreit, one of the authors of the Attention is All You Need paper, giving a talk. And I think this was around 2017 or 2018. And he wasn't a keynote speaker. It was like, the Transformer paper was still quite fresh. And he was giving a talk in one of these like side sessions. And I remember I went to this session out of just curiosity, and there was like, 200 people like crammed into this like room. And I'm like, what is this? Like, this is like, there's something unusual going on. And he gave a kind of nice talk about like this idea of self-attention and things, and why they thought the transformer architecture was going to have impact. And by coincidence, one of the clients of the startup I was working at doing the topological work, they said, we actually have a problem that involves NLP. Could one of your people look at this? And so it was essentially what they were like a medical device company that essentially they had to have a way of showing compliance with various regulations. And to do that, they had PhD students basically reading papers and papers and papers to extract lots of, say, information about the device, and then the demographics of the patients that were tested with that device. And this is a very manual, painstaking process. And so the question was, could we train like a model that could extract automatically at least the demographic information, stuff from tables, things like this, and then make their job a bit easier? And so I basically was like, okay, what do we need to do for this? Regex isn't going to cut it. And about that time, Hugging Face had just released PyTorch pre-trained BERT. And this was like a very minimal library with just a couple of scripts. And one of those scripts was extractive question answering. And so I was like, we could probably use extractive question answering to sort of, get the spans of the text where, the patient information is described and so on and so forth. And so we fine-tuned BERT, which was the only model available at the time. And this gave, I think, pretty nice performance, much better than anything we'd been able to do with heuristics. And so I started thinking, oh, transformers are like kind of cool. And this is again back to my old days of like, Kaggle, like fine tuning models and stuff. And so I remember I was like, okay, I want to learn more, but there was like no resources for this. It was essentially, I think Jay Alamar had his like very famous blog posts, like the Illustrated Transformer, and Sasha Rush, who's a professor at Princeton, had the Annotated Transformer, which is like essentially going through the whole attention is all you need paper and like step by step mapping equations to code and so on. And I went through these resources and they were very helpful, but I felt as a practitioner, I was like missing lots of like details. So like, this extractive question answering like task, it's quite complex, like figuring out how you do all the processing and so on. And I was like, okay, I don't understand that. And then I don't understand also like, how does fine tuning really work? All these kind of things that were kind of relatively new. And so my friend and I, Leandro, we were chatting and I was like, there's something missing like in the middle. And we said, okay, maybe we'll start writing some blog posts of our own because we were both, working as data scientists and machine learning engineers to sort of explain how you actually use this in the real world because we felt the technology was quite new. And we wrote, I think, maybe a draft of a blog or two. And then I got ambitious and said, well, why don't we just write a book? We've already done 2 chapters. Let's just go the full way. And Leandro was like, yeah, why not? Let's do it. And so we basically prepared a draft proposal for a bunch of publishers. And my wife said to me, oh, you're always talking about this company called Hugging Face and, Transformers and stuff. Maybe you should ask them if they're writing a book or if they want to collaborate because, if you do all this work and then they release a book, it's going to be kind of, not so great, right? And so I cold emailed Tom Wolfe saying, hey, we're writing a book. We're big fans of Hugging Face, blah, blah. And I was expecting like no reply because, these are things that like, you're some unknown data scientist and Tom is like the creator of the Transformers library. And he replied a couple of days later, said, yeah, let's have a chat. And he read a few of the drafts that we had done and he was like happy to take part. And so we actually started our kind of, let's say, first contact with Hugging Face through this book project. And I think it was maybe 8 months or 9 months later, Hugging Face, I think, got the Series B funding. And that's when they started really growing the team. And we had a chat with Tom and he's like, this has been kind of fun. Maybe it's nice to, do this more formally. And so we kind of joined Hugging Face without any sort of clear role in mind. But it was like, well, maybe we can do some fun things together. And so my first, I would say, couple of projects at Hugging Face were very much focused on the open source side. So I was a contributor to the Transformers library, doing like inference optimization. And I also worked on several projects around evaluation. And then, at that point, there was when ChatGPT came out, they were forming a kind of small team to see if there's a way to replicate this with open source tools. And then I was like, okay, that seems like the kind of project I want to really dive into. And so for the last sort of year and a half, I've been, fully focused on, figuring out how do you fine tune LLMs efficiently, and then sharing that knowledge with community.
Okay, so let's dive into the book first. What was the book about? Was it more focused on BERT? At what time did you write it, and what is it about?
Yeah, so we started writing the book. I think it was around 2019.
Okay.
And at this stage there was BERT.
So pre ChatGPT, right?
Yeah, long before. And so there was basically BERT, GPT-2, and I think T5 being like the most prominent open source models. And we wrote the book with data scientists in mind, people like ourselves who were basically, practitioners, but we're trying to understand, for various like use cases like summarization or, named entity recognition or these kind of tasks, what are the sort of best models that you can use at the time, and how can you use the sort of Hugging Face ecosystem to fine tune them. And we basically structured the book roughly so every chapter is more or less targeting a task that you might encounter. And there's even a very ambitious chapter where Tom was like, well, maybe we can actually pre-train a model from scratch. And so we also showed at the end of the book like how you could pre-train like a kind of GPT-2 like model. And it's funny because I remember thinking like, oh, this is like not many people are going to need to know this. It's like, we've got all these other models. They seem kind of good enough. But indeed, that chapter was quite prescient. And you can see nowadays that like pre-training is like a very, very big topic for many companies that are trying to figure out how can they, train their own models. And yeah, that was essentially the sort of main structure of it. And all of the other things that we were like heavily inspired by were like the Fast AI course and the Fast AI book by Jeremy Howard and Sylvain. Because what they had done was they had also shown us like, if you write a book with code that is like easy to understand and can be run, it also lets people, better understand how these things actually work. And so we spent a lot of time just making sure that, all of our chapters are kind of like self-contained. You can run them on a collab and so on, which, adds another element of constraints. But yeah, pre-ChatGPT. And then the book was published, I think, at 2020.
Okay.
And that was, maybe like 8 or 9 months before ChatGPT. And I'm kind of glad we did it then, because I think trying to write a book now about LLMs would be very hard. I mean, every week there's a major breakthrough in some sort. And that I think would be quite stressful.
Did you know when you wrote the book that large language models would be the future and would be so popular?
Absolutely not. I would say personally, like, I think, so GPT-3 came out, I think around that time, or just before we published it. And I remember like, it was very impressive as like, you could few shot prompt it and things like this. And it was definitely something that, I had never seen before. But I failed to see the extension of like, okay, you can build a chatbot that is not only like able to chit chat about the weekend, but is also able to say help you with programming. I totally didn't see that development, and I think Leandro was actually a bit ahead of me, because I remember when he joined Hugging Face, he's my co-author, and he said to Tom, I really think reinforcement learning with LLMs is like going to be a big thing. And, he'd built a kind of like a side project doing transformer reinforcement learning. And Tom was like, oh, no, yeah, reinforcement learning is so hard, doesn't really work. I think, we shouldn't prioritize it. And, then of course you get RLHF. So I think even perhaps Tom himself didn't necessarily see this bombshell landing. And I think, it's in many ways, right? If anyone had seen it coming, they may have done it themselves. And I think that shows you a little bit the good thing OpenAI does is they're quite good at sort of seeing the future.
And so what are the big differences for you between BERT and those early stage transformers and what we've got now? What are the differences, and what makes GPT-4o or GPT-4 whatever better and more powerful than BERT and early stage transformers?
Yeah, that's a really good question. So I think the biggest change that I've seen is that when we wrote the book, encoders, so models like BERT, which are very good like at representing text as features, this was, I think, maybe the main focus in industry. So it was like, okay, how do I build like a really good classifier? How do I build a really good embedding model so I can, do like some sort of search on my documents? And the sort of generative models like GPT-2 and T5 and so on, I think they were often like kind of like cute, like, you could write poems, but, you couldn't do too much super useful stuff with generative models. And what I think has been the biggest shift has been essentially the transition of now decoder models, the language models being the kind of main sort of game in town. And the encoder models have become somehow like, let's say, less interesting or, less impactful. So you don't see too much kind of, releases or research now anymore around encoders. And the other big change is that when we wrote the book, I think the biggest model available at the time was maybe GPT-2 XL, which was a couple of billion parameters. And that was already like, oh my God, it doesn't really fit in Colab super easily. It's like super slow. And now we have models like on the Hugging Face Hub that are like 200 billion parameters. And thanks to many innovations around, compression, you can even run these on your laptop. So I think that's been like the biggest shift where like things that were thought to be large and very hard to do have become, suddenly much more accessible for the average practitioner.
So can you explain what's the difference between the encoder and the decoder architecture?
Yeah, sure. Yeah, so when you basically do this pre-training phase with language models, you have a few choices in the design of the architecture you can make, and they have different trade-offs. So the sort of simplest one is like the decoder architecture, and what you're doing here is you're essentially feeding in a span of text into the model, and you're asking the model to basically then predict the next token or the next word in that would come from that sequence based on what it's seen in the context. And so they're called kind of decoding because you do this kind of like auto-regressive, like step-by-step way of building out the response. But fundamentally, it's like this kind of auto-regressive language modeling that distinguishes the choice there. And the transformer, one of like the decoder transformers are just one particular example of a decoder. So before that, we had LSTMs. You had basically decoder LSTMs, which could generate text as well. And then you've also got these like new fancy variants called state space models or Mamba and so on, which are like these like, next generation architectures, which are also decoders, but they use a very different way of processing the inputs compared to transformers. So on the encoder side, it's a different approach where you say, well, I don't actually want to generate text per se. What I really care about is having a good representation of my input. And that representation is fundamentally, some vectors or some embeddings. And the way you can actually build such representations is using a different objective, which is called masked language modeling, where you feed in the full input. So instead of asking the model to predict, the next token in the sequence, you just feed in the whole sequence. You basically mask out elements of that sequence. So if you have a sentence like, I don't know, my name is Lewis, you might mask out the word name. And now you get the model to now predict what would be the missing token in that sequence. And so thanks to the way self-attention works, this basically gives you a representation of the full input sequence, which through the course of training gets progressively better. And now you have essentially a really, really good embedding model. And so these embeddings, they can be used, as I mentioned before, for creating like, vector databases that you can search over. But they can also be used as like feature extractors. So, maybe you just want to kind of extract all the kind of representations from your data and then train like a very light classifier on top of it. So they have that kind of more applied practical sense, and they distinguish themselves by basically not being a generative model.
Okay, very clear. And then I've also heard of encoder-decoder architecture. Does that also, can the two be combined together?
Exactly. So this is kind of like the best of both worlds. So the famous example is T5. And the nice advantage of these encoder-decoder architectures is that they're quite flexible in the types of tasks they can solve. So previously, you kind of had to make a trade-off of like, okay, if I want to do classification, I should train an encoder. But if I want to do generative tasks, I now need to train a decoder. And the encoder-decoder architectures, they let you do a little bit of both, where essentially what you do is you train the two components together. And in the process of training, what's happening is now the inputs that you're going to ask the model to predict the next token of, they're going through this encoder, which is generating the representations of that input, and then it's feeding it into the decoder part, which then does the generative aspect. At the end of that training, you can now just either use the full thing as a generative model, and you can say like, classify these documents, and you just have to sort of indicate with some prompt engineering how that happens, and it will give you a very good output. Or you can just throw away the decoder part, and now you have a very good encoder as well. So you kind of have a bit of flexibility where you can use it in these kind of different manner. And I think, like, at least from what I've seen in the academic literature, like the encoder-decoder models tend to also give better performance on, certain benchmarks. But I think the reason like they haven't, let's say, become the dominant architecture is just because they're a little bit more work to train. You have more parameters to deal with. And, given that the decoder models already work kind of so well, maybe you just keep scaling it. But as far as I know, like only one company, like Reka, who do like multimodal models, I think they're the only one that I've seen that uses like an encoder decoder. But almost everyone else seems to be using decoders today.
And okay, so I'm keen to go a bit deeper into Hugging Face and what you're doing there. You mentioned you're working on fine-tuning LLMs now. It's been a year and a half since you've transitioned to this role. So can you talk a bit about what you're doing today and your current role now?
Yeah, sure. So I'm now a member of like the research team at Hugging Face, and the way we do research is a little bit different to other labs. So in like Meta or Google and so on, the sort of primary output of your work is typically a paper, so an article that gets published in Europe or something. Whereas at Hugging Face, our kind of objective and our mission is to produce tools, artifacts, and knowledge for the open source community to build on. And so in my particular team and my role, it's about how do you take all these different kind of, let's call them fine-tuning algorithms. They have a fancier name like alignment or, post-training, but basically it's fine-tuning. And all these different algorithms, they appear, almost every day, almost every week at least. And how can we take this kind of fairly dense mathematics, which is coming from academia, and how can we kind of bring it into the open source ecosystem so that then people can kind of choose amongst different algorithms and also understand which ones work better or, the trade-offs. And so a large part of my role is around taking these algorithms, bringing them into a library we have called TRL, so Transformer Reinforcement Learning, and then doing a lot of experiments using the Hugging Face cluster to sort of figure out which of the algorithms look more or less promising than others. And one kind of nice example we had of this was the sort of most common algorithm that everyone uses is called supervised fine-tuning. It's just fine-tuning. You just basically take some data you have some, if you join a chatbot, you just have, your prompts and your completions. This works really well most of the time. And then there was this like new algorithm which came out from Stanford called direct preference optimization. And in their paper, they had done a couple of experiments using like small models, like 2 billion parameter models, showing that it worked, better than supervised fine tuning. And in particular, that it was competitive with reinforcement learning, which at the time was quite hard for the open source community to make work. And so we added it to the TRL library. That was my colleague Kashif. And then we ran a lot of experiments using the new Mistral 7B model that had just landed on BitTorrent. And so we saw like very quickly, like I think in a day, that this direct preference optimization gave much better results than just pure supervised fine tuning. And so we then, released the model, but then we also released the data sets we used. We released the code, the recipes, basically how to train it. And this, I think, has now led like the community to now integrate like this DPO algorithm into their kind of toolkit to sort of, get this next sort of step of performance. And so in a sort of general day of what I do, it's more or less like trying to read the literature and figure out, what looks promising. And then trying to find like which base models and data sets and like, the combination of things can produce something that is like kind of interesting and exciting for the community. And what I'm doing specifically right now is I'm working on the AI Math Olympiad. So there's a big challenge to basically see if we can train LLMs to kind of reach the competitive level of mathematics for high school students. And there's an ongoing Kaggle competition. So I've almost done a full circle. I'm competing in a Kaggle competition, both with a nonprofit in France that is helping us build the data set, and also with some guys at Mistral. And the goal is to sort of, open source everything in our process so that at the end, the community can, learn how to build really good LLMs for mathematics. And I'm pretty excited to see, where that goes, because I feel like reasoning and mathematics are like the frontier of like LLMs, where even GPT-4 often struggles to solve, high school problems.
Okay, and so your goal, you take basically pre-trained models like Mistral 7B or models that are already out there, and you want to fine-tune them for specific tasks. using algorithms like DPO, for example. And two, you want to make this publicly available such that people can easily fine-tune other models or the same model for other tasks. Does this summarize as well what you just mentioned, or is there something missing here?
Yeah, so basically it's exactly what you say. It's there's often a fair amount of experimentation that is needed to find a recipe that is like going to work kind of most of the time. And the reason why it's a bit tricky today is because all of this like post-training often involves multiple steps. So, first you might train a model, say for chat, that is good at, answering questions using supervised fine tuning. But then you might want to say, okay, I want that model to like also be, let's say, good at code. And so then what you want to do is you want to say, okay, how do I kind of like get rid of the errors that the model is making at programming? And so then you might use a technique like DPO to basically, you generate data from the model. You then use that generated data on those programs to sort of filter out the ones that you label them as incorrect, and then the ones that are correct. And then you can use these like sort of post-training techniques to kind of push the model gently to kind of statistically get better at producing correct programs. And doing that is like a lot of experiments. Like I would say on a given day, I probably train maybe like, 30 to 50, experiments. And you need compute for that. And part of the process of what we do is to try and kind of save the community some of that compute where like you can say, well, we've run lots of experiments. This seems to work best. Here are some sort of general settings that you can use. And
then you release a doc. You also release a notebook or some code such that people can reuse the codes. Is that the output of your experiments and your work?
Yeah, exactly. So we have a library, or not a library, more of a repository called the Alignment Handbook. And in this handbook, we provide a series of recipes that kind of target different types of base models and also, different types of applications. So an example is like when StarCoder 2 was released by the Big Code collaboration, there weren't any sort of like good coding fine tunes of it. And so we thought, okay, let's show the community like, which data sets are kind of good for that. So we did a lot of exploration in that respect. And I remember when I think it was Gemma. When Gemma came out, Gemma 7B or 8B, a lot of the part of the community had a lot of trouble fine tuning this because it had like a very different kind of, let's say, character to the Mistral models. And so Philip Schmidt and myself, we said, okay, let's provide a recipe so people can then use that. And so that's the kind of work that we do. And I think my feeling is that the academic community is kind of, let's say, roughly converging on like a sort of set of algorithms that are like quite useful in different ways. And I think what is perhaps more interesting in the future is like there's a lot of like work being done now on producing like pre-training data sets. Mm-hmm. And so what you can do with these data sets, you can actually filter them for like domain specific tasks, like, mathematics, for example. And I think building out those domain specific subsets, which you can then use to say augment an existing model. So if you take Llama 3, you could potentially continue to train it on like 100 billion tokens of math data. And now you've got a really, really good like Llama 3 model that can do mathematics. And so I think that's probably going to be the sort of, trend of like the community, and also part of our work will be, trying to bridge that gap so that a lot of the kind of, let's say, techniques and methods that, the kind of proprietary companies have are available to other people.
Okay, so there is the model, and then the two important things is one, the data, because you need some data if you want to augment a model with a specific skill set. And there is also two, the algorithm that you use to fine tune that model to make it learn this new data or this new task. And from what you said, DPO seems to be the go-to nowadays. Is that right?
Yeah, I would say DPO has become maybe the standard thing you do after SFT. And I think it's mostly because it just works usually. Like it's like it doesn't require a lot of like
Okay.
tuning. However, there's been, I think, a couple of very interesting developments. So there's a paper again from Stanford called Kahneman-Tversky optimization, and what they do here is they bring ideas from behavioral economics into like the kind of LLM post-training process. And they found a very clever way where when you're doing this procedure, usually what you need is you need to have a prompt, and then you need to have like 2 or more generations from the model that have been rated somehow. So an example is like, maybe I ask my language model, how do I write a bash script to do something? And then the model produces a few different programs. And then you can check, okay, which one of those ones was correct? And then the ones that are incorrect, you can sort of say, okay, they're the rejected ones. And then I use DPO or whatever on top of it. So you always need this kind of like binary preference data, or like, ranked preference data. And the challenge with this in practice is it's often expensive to acquire, because you typically need human annotators to talk to your model, prompt it, and then rank the outputs. And that's actually intellectually quite a difficult task. So this Kahneman-Tversky optimization, it frames the problem in such a way where you no longer need the relative rankings of the labels. And so in particular, all you need to know is whether or not this completion from the model has been labeled as desirable or undesirable, independent of any relative preference. And so the very exciting thing about this is you can now do something very similar to DPO, but you can just do it on data that has been labeled as good or bad. And this is actually quite easy to do, right? Like when you talk to ChatGPT, you see the thumbs up, thumbs down label. You're essentially, I think, providing similar labels for what they're doing. And then you can kind of continually improve your model by using those labels, rather than having to pay or internally set up a human annotation process for that. So I think that's one side of it. And the other side is like DPO itself has certain flaws that the community has discovered. So for example, it tends to produce language models that like to really talk a lot. So they they produce very long outputs. And, for some things like poetry and stuff, this is good. But, if you want to have like a kind of shorter, more focused response, you need different techniques. And so there are sort of new algorithms that have come out which try to address those elements. And there's even other ones which have tried to basically skip the whole supervised fine-tuning step altogether. So instead of having to do this like 2-stage process, you basically just take a base model and you immediately fine-tune it on your preference data. And there's a cool paper that I've collaborated with the researchers on called odds ratio preference optimization. And they do this. It's very memory efficient, and it's very effective. So that's lots of ideas happening in the 3 week.
Okay, cool. Thanks a lot. We'll share some of those in the description. But yeah, super interesting. And yeah, didn't know all of this. Well, I knew about DPO, but didn't know about all those other algorithms. So thanks a lot. Learned a lot from this. Let's move on to the last part of the chat. Just want to ask 2 questions on your career before we finish the episode. The first one is, well, this show is called AI Stories. So I'm keen for you to tell us a story about yourself. It could be a mistake you've made, something funny, a lesson you've learned, something you've achieved, a success, whatever, but just one story about you.
I guess I can give you a couple like short ones. So
yeah,
I remember when I started this first startup, and I think it was in my first week. So I was working really hard to try and make a good impression. And when you have these Kafka streams, you basically, it's a distributed framework. So you have a bunch of like sort of worker nodes, and then you have essentially like a login node, which is like the controller that is kind of checking and orchestrating, how to mitigate nodes failing and stuff. And typically, these streams are huge. They're like, terabytes of data flowing like every second. And you want to have very good, machines to process that. And then you want to have a small machine for this like kind of orchestrator, because it doesn't need many resources. And because I was like new to the field and I didn't even really know like SSH or anything like that, it was Friday night, and I was trying to finish like one of my first tasks, and I logged in to the controller like machine, and I was trying to basically pipe this huge like fire hose of data into this like tiny, controller, and it basically took down the whole cluster. So like everything was like failing, red alert all over the place. And it was like, I don't know, maybe like 9 o'clock or 10 o'clock on a Friday night. Everyone had gone home. I was like the new guy. And I remember thinking like, that's it, I'm done. Like I'm going to be fired. And I had to ring the CTO at like 10 o'clock at night saying, hey, I've taken down the whole cluster. And, he was very gracious and he said, don't worry, we'll figure it out. And then, just on the phone, we were able to, restart things and get it back to normal. And so that was like one of those things that you make as like a first, your first job. And you're like, oh my God. But on the other hand, it was like, I think, a good learning experience, which is this common story you learn later that you should never do things on Friday in prod in the evening. And so, yeah, since then, I only break things on Monday morning when there's enough time to recover.
Yeah, good lesson.
Yeah, the other thing that is not so much maybe of a story per se, but like one of the nice side effects of working in open source and writing a book and so on is that when you meet people in real life, you often hear the impact that, this piece of code you wrote or, this part of the book that you wrote had on them. And that's like a really special sort of thing that you don't always know, right? Like you don't know if your work actually helps people. And when you find out that, this like algorithm or this recipe, really helped us, solve this technical problem. I think that's like a kind of cool side of the sort of unexpected impact of your work. And I think it's also one of the things I often try to encourage people is like when I was like first contributing to open source, it was quite terrifying to like open an issue on the Transformers library or even open a PR because you're like, oh my God, this is like, the sacred code base. And I think like by doing that step by step, I actually became a much better like engineer because you see how tests work, you see how code bases are designed, you see the different choices of designs. And so yeah, my general recommendation is like if you want to really like kind of accelerate your knowledge of like how machine learning engineering works in the real world, open source is perhaps the fastest route to doing that.
Yeah, no, I agree with you. It's a good point to put yourself out there and force you to share things with people, because here you're sharing code, and because you're sharing code, it has to be clean, it has to work, it has to be easy to understand. And so you force yourself to write really clean code. Whereas if you just code for yourself in a notebook and don't share it with anyone, well, you don't care about the code quality, you don't care about naming the variables in the correct way. And so you will learn also, but you won't learn as much because you don't have this thing of forcing yourself to make something super clean, super easy to understand with the best practices. And so putting yourself out there is probably the best way to learn quickly.
Absolutely. Yep.
So let's finish the episode with just one advice. If you had one advice for people to progress in their career, what would it be? Just one advice.
I would say the thing that has made the most difference for me personally has been kind of like always trying to build something for real, in the sense that like you can read like books, you can watch podcasts, you can like this one, or you can do all these things, and they're kind of like say passive learning. It's like you get some understanding, but the biggest shift for me has generally been seeing like a problem that was interesting and then really trying to solve it like hands-on style. So that often involves writing code and either training models or whatever. I think that is like perhaps the most impactful thing is like not to get this kind of like sort of fear of getting started. Just do it. And I remember like many years ago, I did the Fast AI course, and Jeremy Howard had this advice, which I sort of followed, which was like, you want to have this kind of like sort of T-shaped knowledge, which is like you have like something that you've got some depth in, but then you've also, around that topic, you've got some kind of horizontal, interconnected knowledge. And so in the Fast AI course, the way that they kind of encourage you to do that is by basically, pick one project and do it really well. And then in the process of doing that, you will expand that kind of T where you will learn, okay, if I need to do, say train an LLM or fine tune an LLM, oh, okay, now I need to learn how quantization works, or now I need to do this other stuff. And so I think that's like a sort of advice that's useful, especially when you're in a sort of new field, because the hard thing is like there's so much information, right? There's so many topics, there's so many problems to think about or things that you could worry about. And you can often get this kind of like, very scatterbrained approach. And I think what tends to be valued, at least in our industry, is often this kind of depth of knowledge. So can you solve these like hard engineering problems in a sort of semi-independent way? And the only way I think you can get that is by trying and doing it yourself. It's kind of a bit like a sort of chicken and egg problem, but you have to get started to make progress. So that's what I would recommend.
Lewis, thanks a lot. It was great to have you on the show. Have a great evening in Switzerland and hope to catch up very soon. Thanks a lot.
Thanks a lot, Neil. It was a pleasure.